Before I go deep into this problem, I hate to sound like a broken record, but in physics, there's only a few major ideas that once you, I'd say know them, but really you have to understand them. And it's different to understand something than to know something. But what I've been trying to say since about October is that the most important concept in physics is acceleration, because that represents a change in the motion of an object. And acceleration only depends on two things. There's always going to be something about force here and something about inertia here. It has to be this way. That something's going to cause your system to be unbalanced, or else there is no inertia. And if you unbalance that system, how much inertia there is determines the acceleration. So in any problem where you're asked to look at the forces in a system, this ratio will be the answer to acceleration, to how your system changes. Now, the reason why change is so important is because there's no other thing in the universe that more consistently tells us that objects are interacting than to see a change in what they're doing. We don't worry so much about the things that aren't changing. We can count on them. We worry about something changing. That takes us out of our comfort zone. It means something is happening. Understanding change in any form, it should be recognition that the things that control our lives and the things in our life can be predicted and maybe managed. That's why it's so important that we look at the idea of change and why acceleration is such an important concept. For us, there's two ways in which an object can be affected. We know that it has to do with the forces or the torque. That these two things work together to determine whether there's a system that has a change in position or a change in direction. Whether something about its speed changes or something about its angular speed changes. That's what these two are about. This system is connected together. And the way in which it's connected, as the mass falls, is going to cause the pulley to turn. Now, all the way until this unit, pulleys have been massless, and therefore they have not contributed to the inertia of the system. But we understand a little bit better now that rotational inertia exists, which means trying to spin something doesn't mean it just automatically spins, that it's going to fight you if you try. How much it will fight you depends on its inertia, and some objects fight harder than others. We know the disk is easier to spin than the ring. The ring fights more. We know that having the box hung from the edge of the pulley affects how much torque there is on the pulley. But we also know that how much of a box we hang makes a difference on how much the pulley will turn. These three things that I'm putting on our picture here represent givens. This is the given information. And throughout the course of this problem, I'm going to always write the given information in yellow in our questions. And the reason is to make sure you understand that our answers have to contain the given information and nothing else. Some information we can have in our answers and some we can't. In a few moments, as we look at this, we're going to have letters written everywhere. One of the things I think is difficult for you guys as students is to see beyond just the equations and the letters to understand what it means. And that's a really, really hard thing to ask of you, especially at this point in your lives. I mean, specifically, 6th period on a Friday. It's hard. Most of you are thinking of other things. If you really want to get something out of today, be here in the moment. Be one step ahead of what I'm writing on the board. Now, again, what I'm about to do with you guys in this problem is something you have already done. The most likely example I can point to is to remind you of this picture. Do you guys remember that picture? The box hanging off the table caused the system to move, but the two boxes together were the inertia of the system. When we did this problem, we looked for the acceleration. When we did, we found that the mass that was hung was the unbalanced force. But the two masses together determine the inertia of the system. So if you remember way back, we did this question. The reason I bring it up is that's the question we're doing right now. This question we're about to do is exactly the same. The system doesn't just fall with an acceleration of g. The pulley is hard to turn. And because the pulley is hard to turn, it determines how fast the system's going to move. Now, this is a dynamics question. In all dynamics questions, we are asked to apply Newton's second law, which means we're asked to take a look at the net force being equal to ma and the net torque being equal to I alpha. What I've told you guys so far this year is that when you are forced to do a Newton's second law problem, you have to take both of these and apply them. That's what I said on Monday. But the truth is you don't. You guys are better. You understand a little more than that. Is the pulley going to change location? If the pulley's not changing its location, then you don't have to worry about this. The only reason that would ever come up is if I asked you how much the support has to pull on the pulley. But the support doesn't cause a torque. It's not causing the pulley to change location. The pulley is just staying there. At the same time, is the box going to start spinning due to the forces that are acting on it? If the box isn't going to start spinning, then I don't have to worry about torque when I look at the box. So although it is true that I should apply both of these to each object in my system, I can be selective. I can decide to apply the appropriate ones during the conditions that are appropriate. Now, like any problem that involves forces, it's almost always best to start the problem by identifying the direction I want to call positive. That always helps. And I'm going to call this direction positive. Why? Because I think that's the direction the thing's going to go. And I always like starting there. Now, the first thing I want to start with is the box. Because the box is the known quantity. We've done it so many times first semester that I really don't think you need me to do anything about the box. I think you guys are very aware that the net forces on the box have to equal ma. I also think you guys know what forces are acting on the box, in that you could draw a free body diagram for the box and identify the appropriate forces therein. Meaning, draw a free body diagram, put the arrows on it. And regardless of what you actually draw, I want to remind you that mg downwards has got to be greater than the tension upwards. If they were the same size, then the box would just sit there because the net force would be 0. So as I draw this, it's important that I put down that the downward weight is greater than the tension. That's why it accelerates. But I don't want to leave out the tension, because the box isn't just falling to the floor, it's pulling on a string at the same time. Now, that just leads to mg minus t equals ma. Now, I'm writing it like this because I want you to realize anytime there's something I write down that is a known value, it's something that can be in my answer. M can be in my answer. T I created. It wasn't there before. I put it in there because I know that hanging a box on a string results in there being tension. I know the tension is there, but it's not something that was given in the problem, which suggests it can't be in my answer. Look, you guys have done a lot of these kinds of problems in the past, and there's always a few of you who, when I ask for the acceleration, provide this as your answer. You take this and you solve for A. It's just not that simple, I'm sorry. T can't be a variable in your answer. You created it as part of your problem. Only the given can be in my answer. Now G, on the other hand, what does G represent here? Constants, like the acceleration of gravity, are often allowed in your answer. So anything that's a constant, that's something that's used frequently to mean something else, almost always can be treated like a piece of given information. In fact, in most problems, they will say, you may only use I, R, M, and any fundamental constants that you need. So something like G is fine. It can be in your answer. On the other hand, I left A green. That's what I want. I want to solve for the acceleration of the system. It's an unknown. It can't be part of the answer, but it can be on the other side of the equation. A equals, and then everything else has to be a variable that's in yellow. This represents the result of doing the net force on the box. We've done this before. I know you can do this. Now, it is important that we start, expanding, and that's where we're going to go next. We're going to take a look at the net torque acting on the pulley. The net torque on the pulley has got to be equal to I alpha, where I is a variable that we can actually have in our answer. Alpha is also acceleration, so if I ask for the acceleration, alpha could be part of the answer. It really depends. Do I want the acceleration of the pulley, or do I want the acceleration of the box? But I have to handle this net torque part. I have to look at any force acting on the pulley that could cause it to rotate. And again, torque is tough because there's 3 parts to calculating torque. And I have to consider all of it. I have to consider the torque arm that's acting in the system, the force that's causing the system to rotate, and the angle at which that force is applied. Now, some of these are easy. If it's a pulley, the angle's 90 degrees. I don't have to worry about it. That's why pulleys are chosen, because they always have a force that's tangent. Now, since the string is wrapped on the outside of the pulley, that too is relatively straightforward. And lastly, what force is causing the pulley to move? Would you agree it's the string? Now, here's the hard part. If it's the string, the upward tension that was in the box or acting on the box has to be the downwards tension acting on the pulley. That's not a hard concept, but be aware, though, it's the tension that acts on the pulley, not the weight. I'm saying that because a simple multiple choice question designed to see if you're really understanding is to ask about this tension. And a simple question would be, is the tension in the rope equal to, and then I'd have A, B, C, or D, the weight of the box, less than the weight of the box, more than the weight of the box, or can't be determined? I mean, that is a test question, an easy one. And I think I will get a bunch of you writing down that it's equal to the weight of the box, even though we just talked about the fact that the tension can't be equal to the weight of the box. I'm going to prove it on the next test, one way or the other. And you right now are all trying to write a note to yourself, in anticipation of that. But be aware, you need to evaluate the problem. We've already shown in a prior portion of this problem that the tension is less than the weight in this circumstance. All right, now we know that the net torque has to be equal to I alpha, and there's only one torque. The only question I have left is this torque a positive torque or a negative torque? Does it cause the pulley to rotate clockwise? If it does, then it's positive. Let's be careful about positive and negative. And if you don't see where I'm going, I'm just going to hang a box on the other side in our next example. Thus, one of them turns it one way and one turns it the other. All right, so that's about it. I'm going to write this out, and I'll get RT equals I alpha. This is the result of applying Newton's second law to the pulley. All right. Now, let's say that this is a problem on the AP Physics C exam. Every AP Physics C problem is 15 points. There's 3 of them on every exam. The exam is short. It's an hour and a half. This has been one of the exam questions on the AP Physics C exam. And when this was given on the AP Physics C exam, an interesting note is that if you could get to this point, you got 5 of 15 points, which you might be thinking, great, that's a 33%. 8 of 15 points is passing. If you can find 3 more points throughout the rest of the problem, you passed. That's the level of difficulty this is at, but getting to this point is actually the part of the problem that is challenging. I'm going to show you something in a minute that's worth the 6th point, the thing that would get you one more piece of information. They're not going to tell you it's there. You have to bring it to the table. There's 2 accelerations here. The way the problem is set up now, you can't solve for the acceleration without being told which one you're solving for. The most likely acceleration you'd be asked for is the acceleration of the box. Why? Because you can measure it with the motion sensor. It can be an experiment. I can't measure the rotation of the pulley, not with the motion sensor. That's why in the experiment we did, we measured how fast the toilet paper rolled to the floor, not how fast the toilet paper spun. That's why that experiment was done the way we did it. So we want this acceleration. This next part is about figuring out if these 2 things are related, and if they are, how. And I don't think this is too tough, but it does require intuition. Look, the string is wrapped on the outside of the pulley, which means if the box goes downwards a certain distance, does a point on the outside edge of the pulley move the same distance? Meaning if the box fell down 1 meter, would the outside edge of the pulley have also moved 1 meter? If that answer is yes, then you can say that they are linked together in the way that we talked about with kinematics. Knowing this to be true and applying it correctly is almost always worth a point on the AP exam. Substituting it in correctly will be worth the next point, which means knowing to take this and use it over here gets you 7 of the 15 available points. You are 1 point away from passing the exam. Not a 5, mind you, but passing. When we look for points, we look for applying the laws of physics, the idea of physics. Now, I'm going to put this on another page because this has gotten quite a bit messy. I put together the 3 ideas that we had to assemble. We had R times T equals I alpha. We have alpha times R equals A. and we have mg minus tension equals ma. Now, that's alphabet soup. No matter how you slice it, that is just a group of letters. And you're being asked to express meaning here. I know you guys like it better when there's a number involved in the problem. And I know that. But I also know that AP doesn't always want to do that. So you don't always get that luxury. Which is funny because that's why everybody walks out of the AP exam going, I never turned my calculator on. And that means people think that there was no math on it. Now, the truth of the matter is, are we doing math? Yeah, it's all Algebra 1, but this is hard. That's a lot of stuff. And even now, some of you don't know what we're supposed to do. But we're supposed to figure out what A is. We want A in terms of nothing but yellow letters. That's what we want. We've already identified that it's this A that we're looking for, which means we have to somehow assemble these three pieces of information in such a way that A is on one side of the equation and nothing but yellow letters is on the other. And you need to find a pathway to get there. Now, I see a pathway. I think the first pathway I see involves doing something here, eliminating the alpha and putting it in terms of the letter A, which is what I'm going to do next. I'm going to eliminate the alpha. Do you see what I did? I solved this for alpha, which gave me A over R, and I plugged it in where there was an alpha. Now, if you realize what we did, we took three equations with three unknowns and reduced it down to two equations with two unknowns. Alpha is an unknown and T is an unknown. If I want the acceleration, I'm trying to eliminate T. Doesn't matter where I eliminate it, but I have to. Substitution is probably what I'm going to have to do. So I either solve this for T and substitute, or solve this for T and substitute. I've chosen to solve this side for T and substitute. When I do, and I'm going to group the yellow letters together, I get I over R squared times A. I want to group the yellow things together because those are the ones that can be in my answer. Do you guys see that I divided both sides by R? And that got me R squared in the denominator there? Now, some of you should be ahead of me and recognizing that we are now substituting for T in the other relationship. And that's where we go next. mg minus, well, I have I over R squared times A equals MA. Again, it still looks like alphabet soup, but I got a lot more yellow there and no red. What I have now is something that by itself can provide the answer. I need to collect the green letters together. I need to collect the A's. That way I get them on one side of the equation and then I have everything else on the other. And the only way to do that is to move the one term to the other side. Now that I've moved it to the other side, I can collect the A's together. It's the only way to get them by themselves. And although I know you guys have done this, it has been a long time since your algebra class. So I'm going to collect the A's. Now I can get A by itself. Now, stop for a moment. This is not easy. In fact, I'd say there's a lot happening here. Believe it or not, on an AP Physics C exam, all of that math would be worth 1 point. Meaning, doing algebra doesn't get you very much. Getting these three things together, that's the bulk of the credit. Applying them correctly and doing the math, it's not. However, most students, that's the hardest part, is getting that math all churned together. Now, I do want to stop for a moment and remind you of what this looks like. I mean, can you see what I started with? Hidden in here? Look at the top. The top is the weight of the box that was hung. Right, this is the weight of the box. It's the unbalanced force. The bottom is the inertia. It's the inertia of both objects, right? I got the inertia of the pulley right here, and I've got the mass of the box right here. Like everything we talked about this year, the acceleration of the system is based on two things: how hard you pull on it and how much inertia there is. This will give us the exact same answer. It has to. Now, we don't know what kind of pulley we have. If the pulley were a disc, then its moment of inertia would be 1/2 mr squared. If the pulley were a ring, like a spoked wheel, it would just be mr squared. If the pulley were a sphere, it'd be 2/5 mr squared. Do you notice that no matter which one of those I put in, the r's will cancel? That's not an accident. That's because the acceleration is connected to how fast it spins. So, believe it or not, how big the pulley is doesn't make a difference. How the pulley is constructed makes a difference. It decides whether I put 1/2 there, or 1 or 2/5. Go back to Monday or Friday when I had the hoop and the disc, and we tried to see which one made it to the bottom of the table first. Which one rolled to the bottom of the table first? Was it the disc or the ring? The disc was easier to turn. The disc is 1/2. The ring is 1. When I'm looking at I, it's in the denominator. The smaller the fraction is, the less inertia it has. Now this part's hard. You got to really pay attention. I know you guys are losing it right now. I can see it in your eyes, but look. When the denominator is small, the acceleration increases. When the inertia is small, it accelerates faster. When the inertia is big, it accelerates slower. It all boils down to these fractions that are in front of the moment of inertia. That's why they are this way. The sphere has the smallest fraction. 2/5 is the smallest one there. That's why when I plug it in there, the sphere, which is the easiest one to turn, will produce the fastest acceleration. Look, you don't have to know any of the math to answer the question, which of these three will result in the fastest acceleration? You don't have to. Because if you neglect this equation, you should not neglect the idea. Because that's what it states. Yeah, I want you to be able to get the top equation. That's what I want. But if I ask you to explain which one will accelerate the fastest, you should be able to identify from the list that the one with the smallest inertia will have to accelerate the fastest. It is the easiest one to turn. Therefore, accelerates the easiest. The one that's the hardest one to turn, that's going to accelerate the slowest. Because that's where it goes. Now, I understand the level of difficulty here. But now I've done for you the two easiest of the questions. Every other question from now on is going to, by necessity, have to be harder. Because there are no other examples like this. So I want to show you what I will expect you to be able to do. And I'm going to give you a chance to set this one up, because this is where we're going to go next. This is kind of like what's on your homework. Some of these are already on your homework, by the way. Not much different. Different enough. Here's what I would like you to do. I would like you to set up the three equations that will make this work. There are three objects. So I think there are three equations. There's going to be an equation about M1, an equation about M2, an equation about the pulley. What are they going to look like? I think you can do this. I think we also will all agree that this makes a good direction for positive, in that M1 is bigger than M2. So can you come up with the three different force equations that would have to be used to solve this? If you can, you get a B on the next test. If you can't, you're not getting a B on the next test. You want to get an A, you'll have to do a little more than that. Let's look at your work and see what you have there. First, I did need to set up two different tensions. Now, please pay attention to this part. Look right here. One tension is positive and one torque is positive and one torque is negative. If they were the same tension, this would be 0. That's why the tensions have to be different. As the string goes around the pulley, some tension is lost in order to turn the pulley. That's why. So you can't assume the tensions are all the same like we used to. These two should be pretty obvious because we've done enough that are like that before. The one that's being pulled upwards, the tension is greater than the weight. The one that's being pulled downwards, the weight is greater than the tension. But those two tensions cause the pulley to turn. Okay?